Hello everybody. This is the first video I'm making for Signals and Systems, and Signals and Systems is not too bad of a class, but when I learned it, it was very confusing, and so I've decided to go ahead and make another video series just like my circuits lecture series, which you should go check out. For my archival of this knowledge, so that, and I think it's just easier to like talk about this and explain it, because sometimes it can be a little tricky, but generally the concepts are pretty easy in Signals and Systems. So once again, as a disclaimer, this is just my take on everything that I've learned in Signals and Systems, and this by no means replaces any professional, teacher, and I might use some, notation that is different from other professors and stuff like that. So take it with a grain of salt. Anyway, our first topic is going to be phasor addition, which is a very cool way of adding up cosines and sines. So in Signals and Systems, we work with sinusoids a lot because signals are often represented or described with a cosine or a sine. And the classic definition for a cosine or for a sinusoid is, you just have a normal sinusoid. Let's back up. And it looks like this. This is the angular frequency, and this is the phase. And now in phasor addition, sometimes we want to add up multiple of these sinusoids. And we can add up to n different sinusoids. But, if you've taken any trig, you don't want to add up a bunch of cosines together, And you totally can with your trig identities that you've memorized as a high school student. But instead, we're going to use a different method. We're going to utilize the frequency domain and phasors. But first, I want to show you the cool theorem that allows us to do this. And basically, it's just the sum of all of those cosines with some arbitrary constant, a sub k. So it would be a sub 1, a sub 2, a sub 3 equals just some arbitrary amplitude a times cosine, that same frequency. And this is important, and I'll explain it in a minute, plus some arbitrary phi. Okay? So we had an a sub k and a phi sub k, so these guys can be different. And then here we just have one general a and one general phi. And we have the same omega naught and omega naught here. Now, this is really cool because what we can do is turn this sinusoid into the polar form, and then we can just add up the phasor portion, and we can leave out this omega, this frequency portion, and we don't have to add them up. Now, here's the proof. So hopefully you know a little bit about cosines and stuff, and if you guys would like a video on me just going on about Euler's identity and sinusoids being represented in the polar coordinates, I can do that, but there are some videos which I can link here that where I've already done this in my circuit analysis tutorial videos, so you can check those out. But we need to remember that every cosine or every sinusoid can be represented in the frequency domain or in the polar form. And so we're going to take our arbitrary a sub k and phi sub k cosine, and that's going to be equal to the real part, that's a terrible R, the real part of a sub k, e to the j, and then this argument, it would be theta, but we're going to replace that theta with the argument omega naught t plus phi sub k. And now we know that we have to sum all of those up, right? We have a bunch of a sub k's. So we're going to go ahead and sum up all of them, all of the real parts in the frequency domain. And here's the cool thing. This right here, this is identical for every single sinusoid because we have this omega naught. Like I said here, omega naught and omega naught. So for phasor addition to work, you need to work with sinusoids that all have the same frequency that we're working with. They can't be different. If they're different, then this method falls apart. But for now, we're only going to look at sinusoids that have this, that share the same frequency. Okay? And so effectively, we can just leave this alone for now. We can actually take this out of the summation, and we can focus just on this part right here. And the cool thing about this part right here is that it too gets simplified down, and the sum of all of those complex parts, right? The phasor. This is called the phasor right here. This is called the phasor. That's why it's called phasor addition. All of this right here condenses down to just ae to the j phi, where you can superimpose these. You can turn them into Cartesian coordinates using Euler's identity, and then you can add them up and then turn them back into this arbitrary a and this arbitrary phi. And then after that, we get the real a e to the j phi, e to the j omega naught t. And we know what this is, right? We had that just up here. We said that, well, we didn't say that yet. We actually are going to get what we were looking for right here. And so we get a cosine omega naught t plus phi, some arbitrary phi right here, and some arbitrary a. And so this works out. This equation right here is true. Okay. Now let's actually see this in practice with a practice problem. Okay, so for our practice problem, we're going to be given x1 of t, and that's going to be 40 cosine 40 pi t plus 75 degrees. And then x sub 2 of t is equal to 22 cosine 40 pi t plus 60 degrees. Now, the first thing that you want to do before you try to do phasor addition is to check the frequencies. Are they the same? And it appears to be that they are the same. And I actually didn't define the question, but we want to find x3 of t, right? And x3 of t is going to be just x1 of t plus x2 of t. And so we need to use phasor addition so that we can get x3 of t rather simply. So the first step is to get the phasor. And recall that the phasor is just this part, so we just need our a sub k and our phi sub k. And so our a1, our a1 e to the j phi 1 is just going to be, well, we know what that is. This right here is a1, and this right here is phi 1. And then just for the sake of this is a2, and this is phi 2. And so we can just completely ignore the frequency because they're the same, and we can get our first phasor for x1 of t. And typically the phasor is going to be denoted as a capital X1 for its respective time domain counterpart. And so we're going to get 40 ej to the 75 degrees. And x sub 2 is going to be 22 ej 60 degrees. And so now that we have the phasors, which are just simply complex numbers, we can use Euler's identity to turn it into Cartesian so that we can easily add them up. And so we will get x1 is actually equal to 40 times, and I'm going to write this in a different color, cosine 75 degrees plus j sine 75 degrees. And x2 is going to be equal to 22 cosine 60 degrees plus j sine 60 degrees. And then we can actually very easily add. So x sub 3 is equal to x2 plus x1, or vice versa, it doesn't matter. And we're going to get, so for 40 cosine 75 degrees, we're going to get 10.85. And for this portion right here, 22 cosine 60 degrees, we're going to get 11. Plus, now we're going to look at our imaginary portion. Sine 75 degrees times 40 is going to be 38.63 plus j times 22 sine 60 degrees, which is going to be about 19.05. And once you combine like terms, we get 21.35 plus j 57.68. Now we're not yet done. We want to go ahead and convert this back to phasor so that we can actually see, well, you can convert it back to phasor, or you can just straight up put it in the time domain. But we're going to get, so we need to find the amplitude A, and we need to find the phi, the new phi. And if you remember, the amplitude of the amplitude in this case is going to just be the magnitude of this complex number now, because it represents this A right here. We have this A now, okay? And so we're going to get 21.35 squared plus 57.68 squared rooted, and that's going to be about 61.51. And for our phi, we need to use the inverse tangent with the y component first, or the imaginary component on top, and the real part on bottom, and we're going to get about 69.68 degrees. And so you can put that back into phasor form if the problem asks you to. But in this case, I'm asking you to find x3 of t, which is in the time domain. So we need to write it in our cosine form, which is, and now we can go ahead and substitute our frequency that all of these sine waves are sinusoids are operating at. And we now have our arbitrary phi and amplitude. So remember, these are just A and phi. And this is the answer. Okay? And a little sanity check to make sure that everything looks good. So we have the imaginary plane and the real axis right here. We know that every complex number can be written as a vector. And so in our case, we have these vectors right here. And so the first vector we're going to have is this x1, which I'm going to put as blue, like this. And this is x1, and we can see that it looks about 75 degrees, and we want to add x2 to it, and x2 is about 60 degrees with respects to the real axis, and I'm going to make that red. It's a little bit shorter than x1, so it's going to look like this, about. And then x3 is the addition of these two vectors, and if you recall vector addition, from high school or linear algebra, we know that it's from this tail right here and then to this tip right here, and we will get x3. And does this make sense? Well, our x3 has degrees of 69 degrees. That looks about 69 degrees, especially with respects to x1, which was 75 degrees. And we also see that the magnitude was 61 units, and that is much longer, or not much longer, but it is longer than 40 and 22, which we can see is just about correct. So that's a simple example on phasor addition, and hopefully you learned something.